So we continue with the mini course by Frank Trujillo. Please go.
Thank you. Okay, so today we're going to finish the proof of this. So I just wrote these things to remember what we did last time. So this is just the statement of the theorem. So the theorem was just telling us I have some rotation number, let's say, that is of certain type, has some arithmetic conditions. I want to perturb it and say that the perturbations will be analytically conjugated to my rotation. And we were doing this. So I described an iterative scheme of what we were going to do. And basically, I wrote this because I wanted to summarize more or less what we did last time. So I will start by convincing you that this is what we did last time. So let me perhaps just read it and then I will write some more things. So as before, we have some constants. We fix some constants of the rotation number. And this was my perturbation, right? And my idea was to try to conjugate this to something of this kind, again, R alpha plus something. And my whole goal was, I want to make this smaller than what I had here. This was what I wanted to do. And I wanted to do by controlling everything, I wanted to have some estimates. And what I was trying to call your attention to was that if I start defining some domain T of S, I start to lose this domain little by little. So, for example, we solve this equation, and to estimate the norm of this solution, I had to pay a price. And what I wanted to show is where are we paying prices, because at the end, if you look at the statement, what I say is that I have a new perturbation, which is defined in this domain, S minus 6 sigma. So I lose 6 times, I lose some domain. And what I was telling you is that I have to be careful because that price that I pay like this in my estimates, I divide by this thing. So I would like, a priori, this thing to be big so that my estimates are better. But this will be small and I will need this to be converted to 0 when I'm doing an iterative scheme. So we will see all of this. So just let me recall you very quickly how we obtain this kind of thing. So just very, very quickly. So we started with this. And again, this, I had just something here. Then what we did was to solve this equation. And we saw that I cannot solve it exactly, I have to leave something here. The average I cannot remove. I solved this, and here is the first time I pay some price. I have to estimate this in a slightly smaller domain. Okay, so this is the first time we do this, and I told you this was a constant times norm over sigma to some power. Okay, this is the first time I paid a price. Yes?
And the bottom line is the beta surplus, is it phi surplus?
Sorry, this one?
Yeah. You just defined a phi surplus.
Yes, so phi plus will be basically the difference between this and R alpha.
Okay,
yeah.
Thanks. Okay.
So once I had this, I said, okay, I will use this because I want to define some transformation H, which I defined as this. And here, I wanted this one to be a diffeomorphism because this is what I'm using to conjugate here. So the point is that we saw last time that if I wanted this to be a diffeomorphism, I needed to estimate the derivative of this one. I told you this last time. So if I wanted to estimate the derivative of this, again, we can use Cauchy, but I have to pay a price. So I pay a price again, and I can say, okay, this, I choose this, and I can say that this is smaller than 1, that's what I needed, if I assume that this is very small. So if I assume that, for example, this, I will need to assume here that C times the norm of this over this is smaller than 1. Okay, something like this. But I'm just trying to convince you that, okay, I need to estimate this to make it a diffeomorphism. Here I will need some smallness assumption, but this is just why I have to pay a price. So this implies, so once you have this, then this means that really H is a diffeomorphism. So H is a diffeo. So at least I can see it as a diffeo from here to here. S minus 2 sigma to its image. And something that I would like to also assume, for example, from this boundless assumption, I can say that this is smaller than sigma. Why? Because I want something that is very close to the identity. Because then I can say, for example, that this is contained in tau of S minus sigma, and I can try to say where the inverse is defined. So if I know that H in this domain is smaller than sigma,
minus 3 sigma.
no.
So
This will be the domain of the inverse. The inverse is defined, so it's what I wrote there, is defined in T of S minus 3 sigma. Okay? Because what the worst thing that can happen is that I'm sending this strip of S minus 2 sigma to S minus 3 sigma. This is the worst thing that can happen, but I'm sure that my inverse is defined here. Why am I interested in the domain of the inverse? Because I will need to conjugate with the inverse. So I need to, for this expression to make sense, I need to know where it is defined. So at the end, I just try to make sense of this composition. So I want to say, okay, now that I know all of this, in which set this composition is well defined. So if you consider this H minus 1 composed with phi, composed with H, and I want to say that this is well defined. So, well, what I know is that, so the things that I know is that, two things. I can say that H of T S minus 5 sigma is contained in T of S minus 4 sigma. I can show that phi of T of S minus 4 sigma is contained in T of S of minus 3 sigma. And here my inverse is well defined. Okay? So I can say that this is defined. So if I denote this one as this thing minus R alpha, I can say that this is defined here. Yes, and the last time that I will pay a price is because what we didn't do last time was actually estimating this. I just convinced you that I solved the linearized equation. What was left was of order a square of what I started with. So when you want to estimate this, you will be bound to calculate some derivatives, and if you want to calculate derivatives, you have to pay another price. So the point is that if you want a bound, you pay last time some price, so 6 sigma, and you can say that this is more equal, so the bound looks something like this. You will find some constant, divided by sigma, to some power, which is usually bigger, so I wrote the power here explicitly, but what is exactly is not important for us. It's just sigma to some power, so I wrote m, but okay, what you can show is something of this kind, and you get your initial perturbation squared. Okay? So I'm not going to do this estimate because this is a very long estimate where I have to put everything together and it will take me probably more than 1 hour to just make the calculation. But I wanted to convince you that once I solved the linear part, what was left was its order squared. So I shouldn't be surprised that when I put things together, I find here something squared. So what I want to show you today is, okay, here I wrote this as a black box. I wrote it like rotation plus some perturbation. I can conjugate to something rotation plus something smaller. Black box one step, but I'm far from what I want to do. So the idea is now that I write like this in a nice black box way. I want to iterate it and show that I can do it infinitely many times if I choose well my parameters. I can make everything go together and I can go to some limit and try to prove this theorem. So is this CAM step clear for everyone? It's just a summary of what we did last time, modulo of this that I didn't do, but it is, once we have solved this, this is just a calculation. Okay?
Would you please repeat again which was the last technical one, the very last inequality is the.
Yes. So the point is that last time we ended here. We calculated this, and then we had this well defined. And now I want to estimate this new error term. So basically, I need to estimate this. This is what I want to do.
Okay, composition.
Yes.
Okay, that one is
Because now we have all the elements. I know exactly who h is, who h minus 1 is.
just sum all the errors.
Exactly. So the point that you make the composition and then you will express this very, very big equation and you start to put the errors and then you estimate and yeah. But it's only this. Okay. So please, if you have questions about this is the moment because afterwards I'm just going to apply it. So the point now is once I have this, so I want to know, how to iterate this.
Sorry, Frank.
Yes, please.
I'm aware you covered this before, but can you say in words just why there should be an eta squared on
Here?
the right-hand side of the bottom line? Yeah, not worrying about the fact that you're dividing by.
Sure. So the point is that what we found last time, so I will actually do it formally for a second. If you wanted to solve the real equation, it looks something like this, if I remember correctly. It was gamma of x plus h of x. And then I said, okay, I will replace this, so I can just write this as gamma of x plus gamma of x plus hx minus gamma of x. And then I can treat this as something like, norm of gamma times norm of h. And I was always assuming that, the norm of h is comparable to the norm of gamma that you see from here. But of course, you see this basically doubles. Or, sorry, no, it doesn't see it here, no. Sorry, this is the exponent doubles.
And the norm of gamma comes from Cauchy inequality to the derivative.
Yes.
Great.
Yes.
Thanks, yeah. Or Cauchy formula.
Okay. So, you just press this part. So now the point is, okay.
Can I
Yeah,
add
of course.
something? What is the influence of the mean value of this eta at zero? So is it going to some rotation part or?
So this is something very nice that actually,
So it worries me.
yeah, it works. But I was trying to hide it because this, you really need to estimate in this part that this becomes technical. And so for example, this is something that you don't, so I wanted to emphasize this in the other part. When you do the Hamiltonian case, there is a mean part, and this mean part you cannot get rid of. You get rid of it by some other means. Here it turns out that you can show that in this particular case, so in this setting like this, you will be able to show that this mean value, it's really you can estimate it like this. Like so. You can really find an estimate like this, which is not trivial at all. Because if you notice until now, I never used this property. I just said I'm close to a rotation, but I never said my rotation number is exactly this one. I had never said it before. I had not used it before. So for example, just from this, when you assume this kind of property, so if you assume that this happens, R alpha plus this is equal to alpha, you can conclude things, for example, like there exists some point in the torus for which this is equal to 0. Because if, for example, your function was completely positive or completely negative, your rotation number will be different. So, for example, using the existence of this kind of thing, the fact that your alpha is of certain type, that this has to be of the same rotation number, you can actually conclude this kind of estimate. And using all of this. But again, this is not like, this is not trivial. And this is where you really use this, because otherwise I had never used this hypothesis. So I just wanted to emphasize this at the end because there will be some part that will appear. But thank you for the question because it's really important. I mean, this estimate on this one is not trivial and comes from all of these assumptions. Otherwise, I could just play with any perturbation, but then the result will be clearly false because I can just add it's more constant and it will never happen.
You use this assumption at the end of the proof, but it's really used here as well. Okay.
Yes, because the idea is that when you make all the estimates, you will express this as a function of something. And I will need to be able at some point say, but I know that there is a point where everything vanishes. But yeah, I need the existence of this point at some point. It's just that it would be nice to show, but it's very hidden in the end of the technical calculation, so I tried to hide it, but you found it.
Sorry.
No, it's good. I was thinking that, this will be an important thing to speak about. Okay, so sorry for hiding that. No. But I wanted to speak about that at the end. It's good we did it right now. So any other comments? Good? So, once you have this, I want to try to iterate this. So I will try to lose always a part of my domain, but not too much. So I was telling you that I will choose these parameters to go to 0. So if I want to iterate, I have to do something like this. I first fix the amount that I will lose at each step of my iteration. So I will say the size of my domain divided by some constants and square plus 1. Here you have a lot of freedom. You can choose many things. What is important is that when you sum all of this, which is basically how much will you lose of your domain, you need this to be convergent. You want to say that, because at the end, again, the final domain will be something like what you start with minus 6 times the sum of all of this. And the only thing I want is this for this to be bigger than 0. So you have some freedom here. Okay? So I just need to set some parameters. I need to set this. I need to set this equal to s. The domain of my perturbation is always decreasing by some factor Sn minus 6 sigma n. The size of my initial perturbation, I call it epsilon, like this. And I want to bound the size of my perturbations by epsilon m plus 1, which will be just, so usually this looks like what I have, a square divided by something. So I put it like this, to the 3 halves, which actually looks like epsilon 0 to the 3 over 2 to the m plus 1. So it's really something that is decreasing very, very fast. So what is important for us is that in general, whatever you do, if you pick, with this definitions, epsilon n over sigma n to any power that you pick here, this is still going to 0 when n goes to infinity. Basically, this is how I overcome all of this in the estimates, okay? So now I just fix, let me use this for a second. I just make 0 equal to this. And okay, I know how to apply, I can apply things to this one, and I want to repeat, so it will be an inductive argument. So if you start by saying, like, suppose that I already defined this, everything worked out until some step n, define this, phi n equal to r alpha plus sigma n, where this one belong to this one, was more equal than epsilon n. And then what I want to show is that if I assume that my epsilon 0 is sufficiently small, then after applying my CAM step, so CAM step leads to some well-defined phi n plus 1 equal to r alpha plus this plus 1, and with the good estimates, everything will work out. Okay, so everything is tailored just to be able to repeat. If I can make a step, I make the next one, and I go to the limit. So the only thing that I have to do is, okay, if I have this, I apply my CAM step to exactly this one. with this sigma n. So again, I'm just putting n in everything I had here, and I can apply my cam step. Okay? Does everyone agree with that? So a comment that I never made, but is important, is that all of these maps I obtain as conjugation of my initial one. So all of them have the same rotation number. So this assumption that we have here, this kind of thing, is always the same. Yep.
Sorry, so there's no epsilon on the left-hand side. That's a bound on the size of the eta you get.
Yeah, so I'm just calling it. Yes, I'm just calling it epsilon 0. It will be the what I'm naming eta.
Yeah. And the important thing is that epsilon n to the 3/2 is much bigger than eta squared,
exactly.
So you can eat up the errors.
Exactly. That's exactly the thing. So if I apply the cam step just like it is, then well, this cam step tells me that I can find some Hn, which belong to some space like this, T S n minus sigma n only once. And if I define, so I have a norm of this, so let me write it like this. I can bound this like this, and so if I write this one, which just conjugating by identity plus hn minus 1 composed with phi n composed with identity plus hn, and I write this as r alpha plus some perturbation. Then I know what the number of this perturbation is, so I know that this belongs to some space like this. And I know its norm. Sorry, here I forgot to say where. Here's Sn plus 1, so I define it like this, Sn plus 1. And I know that this is smaller or equal than some constant. Let me say sigma to some power. Epsilon n squared. Okay? So the only thing that I need to check at the end is that this is smaller or equal than epsilon n plus 1. And at the end, so if I write it like this, so if I write this as C of epsilon n 1/2 epsilon m plus 1 over sigma m, the only thing I need to show is that this is smaller than 1. Okay, so if I do this, C epsilon n 1/2 over sigma m, and I open up everything, what I find is C of epsilon 0 of sigma n, epsilon 0 1/2 of 3/2 to the n, and probably will find 10 times n squared plus 1 over s. Something like this. But again, the only thing that you need to notice is that this is going insanely fast to 0. This is just n squared. If I pick epsilon 0 sufficiently small, notice that the smallness will also depend on this s, then everything will work out. And this smallness that I fix is independent of n. It's just like, if I start with something very small, my cam scheme can be iterated. Everything will work out. So everything clear? So again, this is just where things become technical. You have to just pick the parameters, make anything, tune things nicely so that you can make it work.
This power m is not changed.
No, so here I wrote it, yeah.
From the beginning to the end.
So this power m depends on the constants that you have at the beginning. Mostly on top, actually. You can just... So I wrote what it is here. It's like, 2t plus 3, but my point is that whatever you get, it will work out. So I just write m and it should be okay, but yeah, if you want to think like 2 tau plus 3, yeah, it's always 2 tau plus 3. Any more questions? Yep.
I think I'm missing where this doesn't work in finite regularity, where the regularity depends on the Diophantine condition.
Yes, so the thing is that how will you get the norm of h when you solve this?
So you're using Fourier expansion, right? And if I have enough derivatives, I get enough decay.
Exactly.
And then what I'm multiplying it by depends on the Diophantine property. So if it's much more differentiable than the Diophantine property, I should still get convergence, right?
So that's the game. But in general, what you will lose, probably you lose like a fixed amount of regularity at each step. That is the problem. So you fix a fixed amount of regularity. You started with say 1,000, but then it's like see, a little bit less. And then this is the difficulty. Yeah.
Yeah, so in a sense here you also have some drop of regularity, but on the level of the width
exactly.
of the band of analyticity.
Exactly, it's exactly that.
Thank you.
Yeah. So what this means is that I can iterate my scheme infinitely many times, which means that so this means that we can define sequences. So we can find sequences like this. So I can find some sequence of perturbations with some nice bounds. I can find some sequence of Hn, which I used to define transformations. Also have some nice bounds. So C where sigma n totals to. But again, in general, when you see kind of this, you can imagine that this is more or equal than epsilon n to the 1/2. So you can be really convinced that this is going to 0. And moreover, you can assume that this is more or equal than sigma n. So everything should be okay. So you can define this identity plus Hn, which are my conjugations, my series of conjugations, and again, these are well-defined diffeomorphisms from here. What did I say here? To sigma n to its domain. Sn minus sigma n. This is a nice diffeomorphism. So if I define this as the composition of all of those, then what I know is that C of n minus 1 composed with my initial transformation, composed with this, is equal to R alpha plus sigma n plus 1. So the only thing that is left for me, the only thing is to convince you that, well, if you know that this converges, the inverse converges as well and everything works out since this is going to 0, if, so it's a big if I can show this for you, then you can tell me that, okay, but then this is happening. And I conjugated my initial one to a rotation, which was my big objective. I managed to do it. And again, so the goal is to say that this actually happens and that this is analytic in some domain. But again, this S infinity is just, if I take it here, S infinity will be just S minus 6 times the sum of sigma n. Okay? So basically, this is what is left to do. Just use all of these estimates to conclude. And again, what will be crucial is that I also have an estimate on Hn, which means I have an estimate on how this is defined. And at the end, bottom line, just if the norms of this converge, you can show that this kind of composition is well defined. So we'll try to go over that bit quickly. So we'll need to erase all of this probably. Actually, maybe I will leave the parameters. I will just put it here. So first, to show this kind of convergence, what one does is try to estimate the difference between this and the identity.
Sorry, but finally you need to prove also that this limit psi is a differ.
Yes.
It's another.
Yes, so the point is that if you estimate
Property.
exactly, so if you estimate the difference for this and the identity, then you know again you can use your criterion like okay, if you write like at the end if I get that this is smaller than 1, let's say,
Okay,
and then you can conclude that yes, it's just like
okay.
Yeah.
You're.
But thank you, because I actually didn't do that, so it's good that you even remarked that this has to be done. So you need to estimate this, and okay, you know that this is just a bunch of compositions, so you know that this is H, I start with 0, yes, H identity plus H0 composed with all of compositions, identity plus Hn minus identity. And then you can do some kind of triangular inequalities here, so I will spare you all the details, but at the end you can write this as smaller or equal than the norms of the composition Hi with identity plus Hi plus 1, compose with identity plus Hn.
So telescopic.
Yeah, so telescopic kind of thing. But then at the end what you see is that what matters is the norm of Hi. So you can say that, okay, but then, since this is again an analytic norm, just want the supremum of all of this, so I just care about what is the norm of Hi. And again, if I assume that I have this kind of estimate, I can say this is smaller or equal than the sum of I equals 0 n of this epsilon n over 1/2, and again, this is just going super fast to 0. So this converges. Okay? And actually you can assume that this is actually very small if you want, because this convergence is small, so actually you are close to the identity, and that's why on the limit you will also be a diffeomorphism. But then to show that this sequence converges, what I will need is to estimate the difference between two of those. Right? This is what I need. So for this I will pick some points, so I want this, so I pick some point, so usually I will need to estimate this in where they are defined, so Sm plus 1, which is the domain where this one is defined. But I already know what I will need. Every time I want to estimate something in general, I have to pay a price. So I know that I will like something like this. You can choose. So I will just pick a point here, Tsm plus 1 minus sigma m plus 1, and I try to make the estimate, so I try to find what will be the difference between this one and this one. So this is just calculation, so by definition of this one, this will be phi n composed with this h and this one, yes, Hn plus 1 minus phi n. Is this what I want? Yes. You can see just as phi n identity plus Hn plus 1 of z, so like this, minus phi n of z. Sorry, here is just a bunch of calculations.
Yeah.
And here you can write this as some integral 0,1 of the derivative of this map. Something like this. So again, this is not very deep, it's just calculations. I write it as an integral. And then what I know is that I could estimate the norm of the derivative if I pay a price. I know the norm for this one, so when you put the norms inside, you can say that this is smaller or equal than norm of the derivative times norm of this. So Sm plus 1 minus sigma Sm plus 1, and then so since I already know that phi n is close to the identity plus something, let me call this big C. I know that the derivative, so the derivative you can say that will be smaller or equal than 1 plus C plus the price that I pay for taking a derivative, which is sigma. So sorry, here's sigma n plus 1, sigma n plus 1. And then I know the norm of this one. I said that this was smaller or equal than epsilon n plus 1 to the 1/2. And again, you can just show that.
So do you use Cauchy formula again?
Yes, to estimate the derivative. Because here I just know that phi is close to the identity, have to derivate and do this, yes?
Is it hn plus 1 of the z inverse inside the integral?
Here?
The thing multiplied by dt for the change of variable.
Hn plus 1?
Inverse. You're probably making a mistake.
No, I think it's this one because I'm just considering like, you know, this map phi n.
Integrated in 0 at once.
Yeah.
So it's okay.
This is the kind of thing I'm considering. At 0 I'm at z, and at 1 I am z plus this one. And then the derivative of this one will be phi n prime z plus this times this one. Yeah. No, I think it's okay. So,
Can you repeat how you found the derivative of psi n?
sorry again.
Can you explain again the last?
Yes, sure. So, the point is that here in this estimate, basically what I can say is that the norm of phi n, since I'm close to the identity, is basically smaller or equal than 1 plus this sum, plus some constant on this domain. And again, every time I take derivatives, I can apply Cauchy. So this comes from this. I should have said that before. Thank you for the remarks. I have this, so when I take derivatives, I have to shrink my domain. I have to pay a price that is divided by whatever I removed. But it works out. And again, this is going to 0, and actually the sum of all of this is going to converge because it's basically the sum of something very, very small. So bottom line is that using these estimates, you can say that we want to erase all of this.
So I'm sorry, Frank, if
Yeah.
I can ask you a question. So epsilon so then goes to 0 faster than sigma n in two ways.
Yeah.
One, you're dividing by a polynomial,
Yes.
and the other one isn't just a number to an exponent, it's a number to the exponent to the exponent.
Yes.
And that's the extra way it's beating it going to 0 is because you need the square root on in the line you just wrote.
So, yes, so basically, I'm not sure if I understand your question, but what I can tell you is that what you need is some decrease that is, you know, always you need epsilon n plus 1 more equal than epsilon n to some power. This is essential, I mean, you can do sharper than this. I mean, this is just to be sure that things work. So you need something like this makes keys of the estimate. But it's true that, I mean, exactly what you need, I don't know if this was your question, is not so clear. And at the end, what I want is to be able to sum all of these things. So I really need that the sum, every time I make sums, everything works out. So I think I will erase this and hopefully not regret it. So what is happening at the end? This estimate tells me that these kind of norms if I sum them all, this is converging. And from this I can conclude, that if I let, okay, I defined it already, but if I take S infinity as S minus 6 times the sum of all sigma n's, again, this was just chosen so that this is greater than 0. I can say that the sequence converges. This sequence converges to some transformation here in some space of this form. Okay? So what Krzysztof was saying was completely correct. So once I know this, I will need to justify why is this a diffeomorphism. Again, I'm not going to.
Yeah, but you did already.
Yeah. So point that then you have to make like estimate distance between this, and you can conclude things like this. And then I just use the fact that if you consider, for example, this kind of expression phi. So where I was composing on which side? Here. If I do phi n composed, so r alpha plus this composed phi n equal to phi n composed. Sorry, no, here was 0. This was alpha plus sigma n. Well, the idea is that then you go to the limit. When you go to the limit, so going to the limit, you find that this composed with this is equal to this composed with R alpha, since this will disappear. And okay, yeah, if you want to make this completely formal, you need to make some more calculations to show that composition of the limits of everything, but okay, I think you will believe me that this will work out, and this work out. And basically that's the proof in the circle case. So, are there any questions?
I've got a more general question.
Yeah.
Is this epsilon 0 in the theorem can be optimized? Do we know something about how well can we make it?
Yeah, so there is some ideas of how good, I mean, if you want, for example, for this scheme, you can really try to estimate, and in general, you find that this has to be smaller or equal than S or some big power that depends on, basically you can say that this is some constant S to some big power that depends on the constants that you picked. So you can say it's over some big constant, which also depends on this one. So you can try to do it like this. The point is that, this kind of method, you can tell me with which epsilon will work, but you can try to find better methods that maybe may give you bigger perturbations. So yeah, telling for which is the biggest epsilon so that you can perturb and still find this kind of thing, this is not very easy. Yeah, really not. At least I don't know if people can do that. Okay? So now, what I'm going to do in the 15 minutes that are left, because since I started with Hamiltonians and I defined, yeah, of course.
Okay, so I thought that I understand why this is the limit is diffeomorphism, but I was wrong. So to know that this is a diffeo, you need to estimate the derivative of.
Yes.
But you only estimate
So what I want.
difference between psi n to the identity.
Yes. So the point is that if you look at this kind of estimate, what you will be able to say is that this difference is smaller or equal than this sum. So okay, there might be some details here.
Okay,
So,
which should be.
so the point is that this is also small.
Yeah, I know. Okay.
And then when you divide, but this is infinity now is a fixed amount. You have a fixed amount of domain, and you can, if you want, you can lose half of it. You can tell me, okay, can I estimate the derivative of this in half of this domain?
Okay, I see.
But there might be a technical thing that I omitted here, but yeah.
I see. Cauchy.
Yeah, it's always Cauchy.
Okay.
It's always Cauchy form. Okay. Thank you for the remark. So, are there any other questions? Because I'm about to erase everything so that you cannot make more questions. So, I started with Hamiltonians, and the only thing I want to tell you about is, okay, how this thing will look in the Hamiltonian setting, where the hypotheses of the theorem appear, And basically that's it. So let's erase everything. So this will be very, very, very hand-waving. I just want to point out a little bit how things look like in the other setting. So just 15 minutes back to Hamiltonian. Let's say we're going back to Hamiltonians. What we had before, I had just some function defined here. I had some flow associated to this function, which was the solution of these systems of differential equations. So let me write it just like this. E prime equal to minus delta of h. And okay, this you could define using some symplectic form, which for us was not very important, just to recall everything we did last time. And I want to do something similar, so I wanted to perturb something that I knew how to solve. So I was assuming that I had a system of this kind, and I have several properties on this. So I knew that n was analytic. I knew that I was assuming that the frequency of the invariant torus was Diophantine. So remember, this was just because the torus Tm0 was invariant by this flow and had frequency omega, meaning that it was basically theta is being sent to theta plus t omega. Okay, all of this was the invariant torus that I wanted to preserve. So theta were being sent to theta plus t omega. And the last thing, I was assuming that this was not degenerate, which I can, let me say it like this, delta n is a diffeo on a neighborhood of 0. Okay. So in case I don't make it, because I don't have much time, the only thing I want to point out is that exactly what you were telling about this average that I needed to kill in the other case, this time I will need some condition like this to kill some average in something. I just want to, my objective now is to just try to convince you why these three hypotheses are needed. And if I don't make it, this was the one that will replace the things that I was telling before. But I hope I will make it. So I think I don't need to convince you that analytic was useful, because all the estimates were analytic, all the team was Cauchy. So really this, I am more than convinced. So what I want to point out mostly is, okay, how this particular condition looks like in this setting. How is this useful when I try to define some scheme? But then, the point is that I never told you how one works in this setting. If I have a Hamiltonian, what is the idea? So, the natural notion for conjugacy in Hamiltonian settings, so how to conjugate Hamiltonians. Well, one does this through something called symplectomorphisms. So, if I have a map like this, some open set of my symplectic manifold, going to some open set of my symplectic manifold, and I know that this is a symplectomorphism. So, what is a symplectomorphism? Well, it's just a diffeo that preserves this, okay, the restrictions, but it's just a diffeo that preserves this. So if you don't like this because you don't want to speak about pullback of differential forms, this condition is actually equivalent to something of this kind. Derivative of this has to be equal to minus some matrix, derivative of this, transpose this, where this matrix looks something like this. 0, identity, minus identity, 0, and this is the m-dimensional identity. Okay, not very important for us, just to tell you that this exists. This is how you conjugate. And what do I mean by you conjugate? If you pick a Hamiltonian here, then you have a very nice relation between the flows. So you can say that the flow associated to H composed with this transformation is equal to psi, hopefully minus 1, this, and this. So basically my flows are conjugated and I am allowed to consider instead of H with this. So the whole game in this setting is now, okay, I know that I can conjugate by transformations of this kind. I start with something like this. I can try to compose it to find a better form, exactly as we were doing before. So now the game. So what is the idea? I start with H0, which looks like N0 of this plus F0 of theta I. And I want to conjugate by this and obtain some transformation like this, for example. And as before, so what I want here, I want several things. So I want this to be a simple automorphism, because that's my natural notion of conjugation. And of course I want this to be much smaller compared to what I started with, in the same spirit. I want to be able to iterate this kind of thing, I want to make infinite compositions, I want to say that everything works. And the last thing is that when I wrote it like this, N1 is different than N0. Before we had always R alpha. Here, this will change. But what I want is that N1 is close to N0. So as close as, probably as the initial perturbation. So why is this? Because I know that I started with N0. So N0 was something that had the invariant torus I wanted. So just to make things simpler, suppose that we started with N0, which was of this form. Omega I plus 1/2 of some matrix. And my claim is, and the determinant of this is different from 0. This is basically saying that the gradient is a diffeomorphism. And I'm just saying if I perturb this a little bit, so any sufficiently small perturbation, so any sufficiently small integrable perturbation of this, has an invariant torus with frequency omega. But again, to do this, I really need this kind of hypothesis. If you want to do it just like this. This is why we need the third thing. And how much minutes do I have left? 5 minutes. So,
I'm
yes.
sorry, but this perturbation isn't integrable, right?
So the idea is that I want to conjugate to something that has an integrable part again, plus something this. Yeah, but of course, here, this part is non-integrable. But I want that this non-integral part to be smaller than what I started with. So the point is okay. I described you again the vague idea. Yes.
Is there equivalent for the rotation condition that you have before?
No.
It's not necessary.
No. It's not necessary. So this I'm replacing by this. So the idea is that my rotation number will be this. And the idea is that the point is that when you perturb, this time you really lose this rotation number. So you really lose this vector. But the idea is that since this matrix is invertible, I can always move and go back to this.
Hereby you have
Exactly, yes. So that's the thing. So the only thing I want to finish with is, okay, I try to convince you why I did this. Okay, why this one? So I try to describe you what we're going to do. I told you, okay, we need symplectomorphisms. How do you find symplectomorphisms in general? So the thing is how to find symplectomorphisms. And the answer is that if you take any Hamiltonian, let me call it F, and you consider, for example, the time one map of this Hamiltonian, this is a symplectomorphism. Any fixed time of the flow is a symplectomorphism. So the game now becomes to define, like, C0 equal to F0. I know who my perturbation is, a small f0, and I need to define an appropriate f0 that will make something like this. Okay? So it turns out that if you take this L0 plus f0, composed with this, the time one map of this one, and here if I suppose that the norm of f0 is somehow comparable to the norm of f0. So, as before, when we were doing this conjugacy, I wanted to do something that is not far. This has a nice expression. So, this has expression like this. So, let me say that this was of order epsilon. So, if I look at this expression and I ignore the terms of order epsilon squared, again, I have to linearize, you find that this is equal to this plus n0 f0 plus order epsilon squared, where I need to define this. This is called the Poisson bracket. So the Poisson bracket of the functions is just something like derivative like this, time derivative like this, minus derivative like this, derivative like this. Not very important what it is. But the point is that this gives you something that you can try to solve. So basically I wanted to find something like this. This is my potential N1. And I need to make it work as N1. And I will not bother you anymore with this, but I just want to tell you that when trying to solve this kind of equation, you encounter these kind of expressions. You want to solve omega times some function, let me call it A of theta. The derivative with respect of theta has to be equal to some function, whatever. And you will need to solve this kind of equations. And very similarly to what we had before, if you want to solve this kind of equation, so you will have to trust me that this is what happens. If you know the Fourier coefficients of this one, you can express the Fourier coefficients of this one, and the Fourier coefficients in this time look something like this. So let me maybe write it like here. I'm sorry, it's not very organized. You will find that you can express the Fourier coefficients of this one. AK will be something like the Fourier coefficient of this one divided by something. So we have, again, these small divisors. And this time they look like this, which is exactly what we have in the Diophantine condition. And this is exactly what we will make everything work. But believe me, this has much more details than the other one, so that's why I did the easy one. But the main problems were in the other one. They will appear here as well in a more complex form, but it's doable. And I think that's all I wanted to share with you. So thank you.
Thank you. Questions?
You said the symplectic morphism, and I'm a little bit confused on what you mean by symplectic here. You define the symplectic, it's invariant under the symplectic form?
So I'm saying that it preserves the symplectic form. So when you take the pullback of the symplectic form, you will obtain the symplectic form.
Ah, right. Okay.
Yeah. So the point is that when you try to write this, okay, what is the pullback of this? You turn out to find an expression like this. So it's equivalent to say something like this. But this is the symplectic part. Symplectic is just because it preserves the symplectic form.
If n is equal to 1, this is just Fourier.
Yeah. If n is equal to 1, it's just area
That's
percent.
easier.
That's easier, yeah.
Any more questions? Could you say something, maybe a particular example in the exceptional set, for example, in the context of Arnold's theorem, what happens if we drop the Diophantine condition?
So if you drop the Diophantine condition, you can build examples where the conjugacy is not even C1, you have nothing. So you can build analytic examples of circle diffeomorphisms close to rotation where the conjugacy is not even C1, so you have no regularity at all. So really, this is important. Now, something that I wanted to comment is, okay, here I give, for example, in the circle case, I always assume close to rotation. But there's a very well-developed theory of, studying the conjugacy of the linearization of circle maps, and then you have many results. So this was one of the first results in the 60s, but then you have a lot of results by Yoko, Scott Nelson, Ornstein, you have many Armand, you have many things, and then you have way more general stuff, like, better Diophantine conditions, you have less regularity, you have everything you want. But yeah, thank you for the question.
If there are no more questions, let's thank Frank again.
I want to ask a technical question. So it seems to me